Today, I'm happy to be joined by a colleague, Suzana Duran Bernardes, who's a PhD student in transportation planning and engineering here at NYU Camden's School of Engineering. She completed her master's with C2 Smart at the Transportation and Planning and Engineering program. And her master's project involved some of the material we'll be talking about today, the development of a novel multi-sensor platform to collect naturalistic cycling data. Suzana focuses on leveraging non-motorized vehicles safety studies through new ways of collecting and analyzing data. Her research interests include traffic safety, intelligent transportation systems, and urban mobility. Suzana, welcome, and take it away whenever you're ready.
Thank you, John. Thank you, everyone, for joining me today. I'll be talking a little bit about my project. It's an ongoing project, so we still have some results coming, and I will talk a little bit about them as well. So to start, I will cover a little bit about the introduction, background, and objectives of my research, and in specific about the project where I developed the multi-sensor platform, which is called actually BeSafe 360. I will talk a little bit about the device architecture and the system architecture, so present the main characteristics and some of the how the development take place. I will talk about the partnerships that we have and some of the preliminary results, and also the ongoing improvements that we have, some of the extra work and the challenges, and of course have some conclusions at the end. So to introduce you a little bit about the motivation and the context that we are working with is, I'm sure everyone, especially now with the COVID-19 pandemic, you can see how bicycles are getting kind of hyped now. It's actually a hype. So you look everywhere, people are talking about turning the cities more bicycle friendly and actually trying to move away from vehicles and congestion into more of a walkable, more cycling city. So you have people are commuting more, people are using more the bicycles for not only exercises, but also just, leisure and commuting. And from 2018 to 2018, we experienced in New York only a 116% increase on bicycle ridership. And New York, it's been expanding its bicycle infrastructure as well. So right now we have more than 1,100 miles of bike lanes, and we have the Green Wave program that is planning to expand that as well. So not only it's with the city, but also you have city bike that even with the COVID-19 pandemic, it was able to expand its system. So you have now 36 new stations that were built last year during the pandemic, and it covers all Manhattan and significant parts of all the other boroughs and Jersey City. And actually, part of my research is also looking into this type of data, so big data from City Bike and other bike share programs, and comparing to other modes of transportation, comparing to transit and vehicles, the bicycle was the one with the least impact from the COVID. So overall, during the year, you had only 5% reduction on the ridership, and sometimes during the year, for example, during summer, you actually had higher ridership during summer than in 2018. This during 2020. So, and they now have actually 20,000 bicycles. So in addition to city bike, you have personal bicycles, you have those rental bicycles, and you have the scooters. So all of this combined, it's moving towards and following the examples of Paris and other cities, is moving towards more bicycle and more pedestrian oriented cities. But the thing is, we still have to talk about the safety for these bicycles and these pedestrians, because Actually, 2019 and 2020, you had more than 20 fatalities for cyclists for the year. So in 2019, you had 29 cyclists that died, and in 2020, you had 21. This is actually going against what the Vision Zero idea tries to accomplish, which is zero incidents. So in 2018, you had like 10, I believe it was 10 incidents. And in 2019, 2020, you have this increase in incidents. So, and even with the expansions of the protected bicycle lanes. So this is something that kind of turns a little light on that there's something that we still need to do to improve safety for these cyclists and for these pedestrians. But there's the thing, while for cars, for motorized vehicles, cars, trucks, etc., we do have a wide range of ways to collect data. For bicycles, this is not the case. For pedestrians as well, it's harder because you don't have an electric system that you can, turn things on. While for the vehicles, you have connected vehicles, you have all that technology. For bicycles and pedestrians, you still don't have that. You have people working on it. I'm one of these people, but you have other people working on it. But for now, it's a little bit harder to collect data from bicycles and pedestrians. So that's one of the ideas why this project is in place. And we try to think of data that will help us understand the factors that influence in the bicycle safety. So thinking about the number of cyclists in the road, street infrastructure, distance between the bikes and the moving and parked vehicles, the trajectory of the bicycles, the cyclist behavior. So all of these are things that we are interested in looking at to improve, to help improve safety, to improve these studies in safety. And we are trying to kind of think of the technology that already exists for vehicles, how to move that into the non-motorized vehicles world, and also using new types of technology, which is especially the cheaper ones. For example, using Internet of Things, and that's the case of our sensor. And we are trying to use cheaper versions of that type of technology. So for example, with LiDAR or ultrasonic sensors that you have in more expensive in applied to vehicles, to motorized vehicles, we're trying to kind of bring that to our bicycles and pedestrians. So it can, like I mentioned, it can definitely be improved by making this data collection process faster, more ubiquitous, and more reliable and inexpensive. So that's one of the ideas. And like some previous studies, especially we have lots of study from DOSA that are looking into that. And so far they have been used instrumented bicycles to collect cycling data. But the thing with instrumented bicycles is that they tend to be a larger equipment that they put in the bicycle and it stays there, and it tends to be a little bit more expensive. So that's something that we try to keep in mind as well, to move a little bit away from that. We are trying not to have something constantly attached to the bicycle that we need to have several bicycles to collect data. And some other studies that we have as well, they look into for example, the acceleration behavior and how these relate to the cyclist safety. And they use some types of sensors. So for example, there are sensors that you can detect when the person presses the brake to understand this type of behaviors. And so we are looking into all these sensors and trying to combine all in one. So for example, it's not listed here, but honk, that this last year this year actually posted a paper in which he actually uses LiDAR for scooters. And like I mentioned, it's also a little bit larger and more expensive because it's a more expensive type of LiDAR, but it is attached to a scooter. And so we started to think, okay, maybe it's something that we can also have our sensor kind of built in a way that we can not only use in bicycles, but also other scooters and other types of non-motorized vehicles. And also, Osbey et al. Shows that the sensors this type of sensors, they are not only used to record the data for later analysis, but you can also use in real-time analysis. So this is also part of our project that we're trying to achieve, is how to make this a real-time analysis as well, so we can actually benefit other, not only researchers, but the cyclists itself and the agencies. So right now, for example, the current methods that we have for data collection for cycling is actually with surveys. So the basic survey, which is expensive, take time, can have some bias. And we also have cycling videos. So the way that the cycling videos work is basically they record videos of people cycling on the street. And then they take these videos and they show to people, different type of people that either never cycled or that never cycled on that place, several different type of people. And they show these videos and they have to kind of rate that experience, the video, if they would feel safe on that ride, if they would feel anxious, stressed. So there are different types of ratings that they can use, depending on the objective of the research. And I still believe that even though it gives you a sense of the safety perception, it kind of still gives you bias, because it's watching a video and experiencing in real life, or having that sense of reality, it's a little bit different. So I still believe that you can have some bias inserted on that type of methodology. Otherwise, it's just using GPS receivers. So actually GPS is part of our sensor, like you're gonna see, but some of the research in the literature actually use just GPS receivers for collecting the data, and it misses some data. So you can get trajectory, but it misses some of the environment that you have for the cycling. They also have video camera footage. So this is interesting, I feel like, but it's also, it can be expensive. You have to either have access to a really good model, or you're gonna expend a lot of money and time on people, so they can actually identify bicycles and identify the vehicles and then understand their interaction. But it's interesting. It's part of my dissertation to look into this type of method, but it still is something that I feel like it can be improved. Other type of data collection that we have so far is crowdsourced fitness apps. So you have data, for example, from apps like Strava, or these other apps. I feel like the Strava is the biggest one, but they do offer cycling data, so you can have access to their cycling data. You can pay for it, which is expensive as well, or they open the access to some agencies, not everyone. But it's an interesting data as well. But I would say that the main downside is that you cannot actually differentiate between commute, and you cannot have sense of the surrounding as well. So you cannot have a sense of the environment, the vehicles that are passing by, or the condition of the road. You can basically look at the trajectory of the bicycle, and that's all. So like I mentioned, we also have the instrumented bicycles, and these are bicycles that everything is built on them. So it's attached to them, and it's going to be those bicycles itself. So you have to build many different bicycles so you can collect data. And the last one, this is a pretty new one. The Federal Highway Association has a project on that, which is the virtual reality. So basically what they do is that they have a stationary bicycle and you use the headset, and it depends. There are some that has the headset, there are some that hasn't. And you have this environment which simulates the real environment, and then from that they can get the data from the bicycle. So speed, you can get the movements, the positions of the bicycles. So it's an interesting one as well, but like I said, it's still very expensive. So you have to create this whole environment, this whole virtual reality environment, and you need to have this lab set up, and it's a little bit more complicated. And then we enter the objectives of my research. So I just wanted to bring the broad objective of my research, of my dissertation, which is, like John said, to leverage non-motorized vehicle safety in urban environments through the use of new data collection modes, especially the ones using emerging mobile sensing and other novel technologies and techniques. And like I said, I also try to look into big data, look into video camera footage, and also I'm starting to look into the virtual reality as well. But those require more time, and those are initial states. So right now, what I bring to you is to talk about the sensor that we've developed to actually make this easier to access this type of data. So talking specifically about the BSafe 360, which is the device, it's basically what we wanted it to be, is it to be an integrated, inexpensive, and highly portable mobile sensing device. So we want to have as many sensors as possible, given the price that we want to keep it, giving the also the computational power that we have. So given all that, we want it to be highly portable and highly, efficient. So it also has a customized software platform for collecting and processing this data. And it can also be used to be as a mapping and warning device for cyclists. So allowing them to choose safer routes and avoid dangerous interactions. So basically, and this figure kind of represented, the 360 idea is exactly that. Have a sensor with a device with several sensors that will give you, a smartphone connection. It can serve as warning system. It can connect to your vehicle, to your motorized vehicle. So, have some sort of communication. So you can also communicate with the infrastructure. And then the data can also be used for planning and policy making, for research. So research like ours in safety, and also in incident management. And I would talk a little bit about that when I talk about the ongoing improvements. And then the route choice, cyclist behavior, and health data, so related to the cyclist itself. So with the health data, we can kind of get the level of stress for the cyclist, so you can actually provide the cyclist with better route choices, and you can also improve in general the behavior that you have, so choosing better routes, safer routes. So here, this is the device, and so in person, usually people like to see it. So I actually put it here. I don't know if you're gonna be able to see it. It's pretty simple. It's just this case, and there's the charger, and everything is inside, and you just attach it to the bike, and there's the GPS. So it's pretty easy to use. It's just attach it to the bicycle like it's shown here. And its component is the Raspberry Pi microcomputer, two ultrasonic sensors that collect the distance. You have the GPS, you have the accelerometer, the gyroscope, and the temperature sensor. These are the ones that are stable. So they're the prototype that are stable. We are experimenting with other sensors. So for example, we're experimenting with cameras and other type of sensors. And the advantage of this one right now and is that the cost benefit. So it's about 200 per unit to build an unit, which is actually cheap when compared to other types of collecting of other methods for collecting this type of data. And like I showed you, it's highly portable. It can be actually, we're also working on reducing the size, so it can also be reduced. Is customizable. So for example, if you like, we have the partnerships and I will talk about it later, but it's something that it can be adjusted. So you can include more sensors, you can adjust how you put the sensors, etc. So it's highly customizable and it can be applied to different, like I mentioned, it has different applications. So for now, the exact stage, these are the data that it collects. So it has some that we don't even use, but the most I would say is that we get the latitude, longitude, which is combined with the speed. We have the trajectory data. We also get the climb, which is actually the rate of ascent and descent. So you can look at the bicycle if it's going up or down, and then that can help you understand a little better how this behavior works in different situations. We also have the acceleration. We have the positions of the bike in 3D. So basically, if you have like the bicycle going like this, if it goes a little bit to the side, we can kind of identify that. We also have the temperature and the readings from the distance from left and right. So how does it work? Basically right now is that you attach the device to the bicycle and turn it on, of course. And when you go out and you just start to ride and you forget about the device. And I'm sorry about that. My street is very busy. So when you go out, you can just forget about the device and it will collect your data constantly. So it's gonna get the positioning, the GPS position and the speed, and in like the image shows, it's gonna get the distance of the vehicles that are passing by and also the vehicles that are to the side. And you can actually identify when it's a vehicle. It with the data, it shows you can identify it. I think I will be able to show it by the end. And then after that, it actually stores the data on the device, but also sends this data into a database that we have. And from there, we can do the processing and all the cleaning. And it can also be sent to our dashboard and the iOS application that we're developing. So a little bit more, so you can have a sense. So you have the data collection, data aggregation, data analysis, and then all the visualizations that we do. Yeah, so here, for example, this is, I feel like it might be a little small, but this is an example of how the data look like. So when you see over there the readings, the US reading right and left, so those are the distance readings. Those are the ones that we're using, the main ones that we're using now. And yeah, like I said, there is also the app for monitoring. It's not okay. It's not being used right now, but it's in development. And we also have our dashboard. So we actually have partnered with different cities. So different universities and a company. So right now we have partnerships from New York to Shanghai, to Brasilia in Brazil, and also São Paulo in Brazil, and Denver in the US as well. So right now, we already started data collection with Shanghai, and we're about to start with Brazil, and probably in the near future, Denver, I believe still this year. So for the partnerships right now, these are the routes that we're collecting data. So we have a route A in Central Park West and B in Columbia University. And then, so this is a mix of protected, conventional, and shared bike lanes, or even some streets that don't have bike lanes at all. These are pretty short rides. They're 2.2 kilometers, 2.1 kilometers, which is about 1 mile, maybe, or less. Yeah. And with China, which is the Tongji University, we have 3 different routes. So we have one surrounding Tongji University itself, which is in Yangpu, where we have conventional and protected bike lanes. And in Pudong, we have 2 different routes. So Tongji, it's more of it's the bike lanes there are more, I would say the traffic is calmer, so it's a little bit different from what we have here. But in Pudong, we actually have 2 different routes that are more urban, and you have conventional and shared bike lanes, so it's a little bit more similar to New York itself. And in Brazil, we have in Brasilia, in the borough of Brasilia, we have decided for a specific place which has both conventional and protected bike lane, but it's a little bit different, which will be interesting to look at, because the bike lane is actually to the left of the road, which is different from here, which is to the right. And also there you have several parking and entryways throughout the route. So this is so you have an idea of the types of routes that we're working on right now. So in the beginning, I just want to present, before I present some of the results between Tongji and New York City, I just wanted to talk about the beta tests for the prototype. That's when we first did our beta test, was in 2019. And we actually used routes in Brooklyn, downtown Brooklyn, surrounding Tandon University. And we collected data for about 3 hours and 20 minutes, with a total of 23.4 miles. And in this, during this time, all the readings that were above 400 centimeters or 4 meters are eliminated because they are over the range of the ultrasonic sensor. So basically, when the ultrasonic sensor is collecting data, it will identify all the objects that are within, that are within the 400 centimeters or the 4 meters. And everything that is above that, you can consider that there's nothing to the side of the bicycle. And then I will show you a dashboard that kind of summarizes, so you can see how this look like. And so the first route was on a street with a conventional bike lane, no turnings, it was a straight line. And we just collected to the right of the right side of the bicycle, and we had 74 records with readings below what we consider to be a safe distance, which is 100 centimeter. And one of these were at an intersection. And the thing about this being in an intersection, and that's one of the, when basically in the beta test, we kind of, okay, this sensor actually can identify some dangerous situations, is that this specific one happening at the intersection, what happens is that the bicycle is coming and somehow a vehicle was gonna come like get to the side of the bicycle. And this is one of the most dangerous interactions between cyclists and vehicles, that it's, when we go to the literature, we have a lot of incidents happening when the bicycle is adjacent to the vehicle, but we have several fatalities when the vehicle actually gets the bicycle in the side. So this was, and this is why I'm presenting the beta test. This is what, when we identified that the sensor actually could be interesting and could be, if it could be a potential device for safety studies. And so another things that we looked back then was the average speed for all these records, which was 4.61 miles per hour. And something interesting is that when the readings were below the safe distance, the speed actually was higher than when it was safe distance. So this safe and unsafe distance, it's based on some states law, which says 100 centimeters. But it's interesting to think about it. This was only one person, but it's interesting to think how the speed can be higher when this person is at unsafe distance. And then you start to think, okay, why is that? And can we actually use the sensor to find out why this happens as well? So all of this came from our beta tests. And here I'm showing you the trajectory and the dashboard that was showing this. So as you can see here, these red points here are exactly where you have the unsafe distance, so below 100 centimeters vehicles to the side. And right here you have the intersection where the vehicle is to the side of the bicycle and coming from the intersection. And other part of the beta test, with more people this time, and also collecting from both sides, it shows actually that you have in general way less readings below the safe distance for the left side, but you have lots of readings to the right side. So with this might indicate that actually these cyclists are cycling more closely to the parked vehicles, which makes sense when you go to the street and look at it, which not always is a safe behavior as well, because you know that it can also happen of a vehicle either leave the parking without any notice, or opening the door, and actually you have incidents, fatalities that come from this in 2019 that happened when a woman was riding the bicycle, someone would open the door and she crashed on the door, and unfortunately it was a fatality. So not always riding at an unsafe distance to the right side, skipping to the right side is the smartest idea. So this is also something interesting that came from the beta test. But here, when you have more people, now you have people with speeds below the safe distance. The speeds are actually lower than when the distance are safe, in the safe distance. So this is an example from these readings right now. And here you can see also the red dots. You can see the unsafe distance to the left side. And also this one actually came with some interesting observations, is that, for example, on this part over here, we had a near miss. So we could confirm that through video, because we also sometimes record the rides. So we can actually see that, okay, we had a braking here, so the person was braking, and we also have unsafe distance, and it all in it's very different from the other places of the ride. So you already identified that something is wrong just looking at the data, and then you can confirm it was a near miss using the footage from the phone. So we're trying to understand exactly how we can do, and then we can automate this type of decision, this type of analysis, and actually tell when it's a near miss, when it's something like that happens, just by looking at the data, with no need, for example, for validation from camera. And now about more recent results, we have the summer 2020 partnership with Tongji, which we had those 4 different routes. We had 4 people collecting data in China for 3 days, and we have 1 person, me, collecting for 10 days in New York City during peak hours in Shanghai and New York City. And this gave us a total mileage of more than 125 miles to compare the data. And each region, Pudong, Yangpu, and Manhattan, we had about 6,000 readings, records from the sensors. And when we look at the different distributions from this that came from the sensors, it's actually that Manhattan, even though they're similar, Manhattan does have a smaller sample size, but not that much. But what we noticed is that in Manhattan, my readings are actually mostly above 400 centimeters or 4 meters, which indicates that most of the time there was nothing to my side of the bike, on my left side. So this is basically saying that it was probably less occurrences of unsafe distance. And when we look at the speed distribution for all the records, we can also see that the speed for my readings were actually more, it was more distributed along the distribution. So you had a higher variance of speed in mine, which can be, there are some reasonings behind that. Could be that it could be that here, because here we have some, the routes that we chose have some high elevation. So here close to Colombia, we actually have some steep streets. So it can be because of that. So you can go during the climb, you can go really slow, and when you go down, you can go really fast. So it can be due to that. And for the Yangpu and Pudong, we can see that they are kind of more similar. So it can be that so that's one of the questions that came from this study that we're trying to answer, is how much of this is actually due to the infrastructure, how much of this is actually due to the behavior of the cyclist itself, and how much is due to environment, like the vehicles that are to the side of the bicycle. So these are all hard to answer questions, even with these data. So we're trying to improve the sensor in a way that we can answer these type of questions. And separating these distributions between the safe and unsafe distance, when we look at the unsafe distance, we see that Manhattan has much lower, or my readings has much lower number of times that these occurrences of unsafe distance. And this might be probably because of behavior, because everyone kind of knows how Manhattan is. It can be tough to cycle sometimes, but it might be because of behavior. It might be because also the traffic wasn't that intense at that time. And for speeds, is also that you can see as well the speed is much lower and has much more variance than the speeds from Yunpu and Pudong. So you can see a much higher, the mean speed it can be higher for Pudong and Yangpu actually. And for the left distance distribution for records at the safe distance, which is let me just show here. In here, you can see that now the distribution is positively skewed. And you can see now that Manhattan does have a little bit higher count and still much higher variance than the other two. And for the speed, we actually see now that the mean and the median of Manhattan is actually coming a little bit higher than for Yunpu and Pudong. And so from that, like I said, several questions came from that, from observing that those distributions and those results. And then we started to think, okay, how can we improve that? How can we improve the sensor in a way that can answer those questions? And some of the ongoing improvements are the vehicle detection. So we're installing cameras to the side of the sensor as well, of the device as well, so we can identify objects, the type of objects, the speed, if it's double parking, the road conditions. So there's a lot that we can take from this. But there are some challenges, for example, improving the model accuracy to seamlessly integrate to the current software platform, and also some of the computational resources that are needed for this type of model. Other improvement, and that's when like I mentioned in the beginning, we have the incident management, and that's when I'm going to talk now. One of the things that we're trying to do is look into the gyroscope and accelerometer data, in which we can identify hard braking and incident. So basically, this is what happened one day. It wasn't anything serious, but I did hit my husband behind his bicycle. So I was in my bicycle. He broke his bicycle, like hard brake, and then I wasn't paying that much attention, so I kind of like hit him. Nothing happened, but I was collecting data at that time. And then okay, something happened. Can I look at the data and see something interesting there? And I actually saw. You can see here in these lines that you do have some changes, some high peaks in between, and specifically for the accelerometer in Z, and the gyro in Z, and also in X. So you can actually identify when this kind of things happen. You can identify when the bicycle hits something, or when the bicycle have some hard braking. It's identifiable, and that's something that's pretty interesting, because if you can actually automatically identify that in a precise way, you can actually send a message to to the correct personnel, to I don't know, first responders, so they can check if it's actually an incident or something. So that's something pretty interesting that I found, and that I believe that when correctly applied, it can be very useful. But like I said, the challenges is precision and accuracy, and also all the noise in the data. And talking about the biggest challenges, my project is specific. This project suffers from two big challenges, which is the data collection. We do have few volunteers. Like I said, it was mainly me. And also the winter weather. So during the winter, we cannot collect data at all. People don't cycle, and it becomes hard to collect data. And also the unit assembly. So basically, it's kind of hard to assemble a big number of units. So it is not possible to do big scale right now, and also the distribution of these units. And now I just want to talk about, this is pretty cool, that came from this work as well, is from the ARISE program. We had some high school students in which they started part of something that is part of our study as well, which is look the effect of the proximity from these motorized vehicles on the cyclist stress level. So we're using heart rate data to actually identify if cars getting close to vehicles actually have some effect on the cyclist stress level, and if we can use that to suggest better routes, for example. And I actually found that it does seems to have a correlation, and then I will be able to look more into that when we collect more heart rate data. Yeah, so that's basically it. It shows to be an all-in-one data collection tool. It was able to successfully collect all this data, and also, you know, contribute to several different questions that can be answered through this type of data. And that's it. Thank you for listening to me for this long.
Suzana, thanks a lot. We already have one question, and I want to encourage all participants to ask lots and lots of questions. Okay, good. We have a couple. That's great. So the first question is, I guess, what guided your decision to create like a independent series of sensors instead of just using some capability inside a smartphone? The smartphone already has things like an accelerometer, a gyroscope, GPS, thermometer, etc.
Okay, so the thing is, when I got here, the basic idea of this sensor was actually collect the lateral distance, because back then there wasn't many people doing this. I couldn't find. So we actually started to look into this distance. And then from there came to the idea, okay, what if we not only collect this distance and trajectory, we also implement other data that can be combined to this type of data to create this holistic approach. So, and the thing is, we can use this data, for example, from cell phones, but I feel like it's more effort that you have to put on to collect this data separately, then combine them, and all this post process that you have to do, than to have all collected at once. And it's cheap to implement these other sensors. So why not already have that instead of having the effort of doing all that afterwards?
Okay, so this question is from Jenny about combining this technology with a camera might be useful for collecting curb data as well. Have you thought about any future applications in that way? Like, for example, identifying double parking?
I haven't thought specifically of me working on that because it's not part of my research itself, but it's an idea that already came from previous work from Abdullah Kurshku. He used to be my supervisor and helped me a lot with this project. But it's one of the ideas that came for this type of using the cameras as well, because during our studies on the literature and also our meetings with the DOT, is that they are pretty interested on that. They're interested not only in identifying double parking, but also identifying the conditions of the road. So I do believe that it can be useful. I myself won't enter too much into deep in that, but I do hope that it can be some data that other people can use to do that.
Okay, this question from Mark about the relationship between heart rate and protected versus standard bike lanes. Have you noticed anything? Can you elaborate more on these findings and any additional data collection you're planning in this area?
Sure. So basically, what it seems like it's that it does have a correlation. We found that it correlates to both a vehicle getting close and to the bicycle, and also, of course, to the elevation. So we do have to kind of differentiate on that. Like I said, we started with their RISE students and their high schoolers. They did find some interesting findings, but we do have to kind of investigate more into that and see if that, so we can actually say, okay, this is due to the proximity of vehicles. But all that that reading all indicates that it is. But I plan to collect more data with this new in this summer, because that's when we try to collect as much data as we can and find volunteers for that. So I do plan to collect heart rate on that as well, and also look, of course, into the data from this the sensor, and I believe that I will also combine speed data from the vehicles and traffic volume. I feel like these are important when trying to understand that if that comes from the heart rate or if that comes from other, comes from the traffic or other type of situation. And so we also collect the heart rate not only during the traffic, but we also collect resting heart rate and walking heart rate, so we can compare and actually have an understanding what is affecting the heart rate or not.
I don't know if we're allowed to advertise for volunteers on here, but if we were, there it is. So I have a quick question real quick before we get to the audience questions. How did you choose the threshold for what constitutes a safe distance?
So the threshold was actually established from the literature, actually law, the law from some states. Some states actually define a safe and unsafe distance. They have written, okay, so if you're getting closer than that, you're gonna be fined. Yeah, but it's something that I want to study as well, because I do believe that this data can actually, confirm that that's the threshold or not. I'm actually doing some work with D Yang, that we're trying to look into safety, surrogate safety measures using this data. And that's one of the things that we're looking into, the threshold. Yes.
We'll actually have D present his work, I think, next month. So we're excited to have that happen. I have a couple more questions and not a lot of time, so we can breeze through these.
Actually, I'm going to try to answer really fast.
No, this is great. So I guess this is regarding your data on average bicycle speed. Are you omitting pauses, like at red lights and stop signs?
To look into the distributions, I actually eliminated the stops.
See if I can get this right here. Is distance data variability also a function of the traffic volume adjacent to the bike lane?
We do believe yes. From the data from the beta test, it seems like yes. We are confirming that, like I said, it's all pretty recent, the data collection from the Tongji and all this, but we are confirming that with Tongji data, because we are also using traffic volume. But before, for the beta test, with that all indicates that yes.
This technology seems obviously relevant to bike share companies and to agencies. What is needed for wide-scale deployment?
Money, I would say, and also, of course, more people volunteering. It's pretty hard to get people to volunteer, I'm not gonna lie. And also people, because I'm the only one right now building the units and developing the software and doing all the development. So that's something that we are talking. So me and my advisor is to now now that we see that this is a real good project, that it can be, a big scale project, we're now considering opening this not having just me do all the development and have people with more experience, for example, in coding, because that's not my background, to actually help us and in the developing, be able to do big scale.
Can you give another example or multiple examples of the kinds of agency or industry decision-making that would be enhanced with wide adoption of this technology?
Yeah, so for example, right now we all know that protected bike lanes are great for improving safety, but it's not something, it's still debatable how safe it is, how much it improves safety, especially intersections where you have people encountering. And so you already have these bike lanes in some places, and okay, so you have some studies on where you're gonna install protected bike lanes next. And this sensor can actually make it more efficient, that decision, because you can look into the routes that are experiencing vehicles getting the closest to the bicycles, and you can see how these dynamics are working, and then you can actually be more targeted on the regions and the streets and the segments that you want to tackle next, that you want to improve safety next. Right now you have this KSI, which is an indicator of which regions are actually not so safe for the cyclists that are happening. So it's based on the crash, but then if we can get based on more targeted data, so for example near misses and dangerous situations and cars getting close, you can have a more efficient decision making on where to address the safety problems next.
Okay, that's
that's
great.
one example.
I think that's a perfect place to stop. So if I may, you can feel free to contact Suzana, right there, in case you want to volunteer, should she need extra volunteers this summer. And if you enjoyed this webinar, we have a couple more coming up. The next one's going to be on, I think, May 16th. And we'll have another colleague, Di Yang, present his research later on in the month. So Suzana, thank you so much. And thanks everyone for attending and for all the great questions. We hope you join us again.